Good afternoon. My name is Eric Hansen. This is Transport 2, homework number 1. The problem we have today is that we have a species of gas A here and an equal volume of gas B here. They're separated by a divider. When we remove the divider, gases do what they do, and they're going to diffuse together. So after a certain amount of time, under constant temperature and pressure, they're going to diffuse together, which I have drawn illustrated right here. The problem that we want to do today is that we want to relate the molar diffusive flux, denoted by big JA here, with the mass diffusive flux, denoted by little ja here. Now, what flux is, I just want to kind of review this real quick. Flux is X, whatever, mass, molarity, weight, anything like that, over an area times time. So what we're looking for in here is going to be, with big JA, it's going to be molar, molarity, or the moles of something, not molarity, over area times time, and then here is mass over area times time. So to start out, I'm going to erase that real quick. So what I'm going to do first is write down the expressions for the molar diffusive flux and the mass diffusive flux here. So to start off, the molar diffusive flux, big JA, is equal to the concentration of A in particular, times velocity of species A minus big V hat. What big V hat is, that is the average molar velocity. So add up all the velocities of all of the different moles, and that's what you get here. To look at little ja here, the mass diffusive flux, we have little ja is equal to the density of A in particular times VA yet again, the velocity of A, minus little v hat, which is the average mass velocity. So the nice thing about what we have here, the average molar velocity, so if you notice that A is going this way and B is going that way, well, they have to go the opposite ways at the same exact time. So when you sum up big V hat, that equals 0. So what can we do with this? We can pretty much drop that out. So when we rewrite this equation, big JA is equal to the concentration of A in particular, and that's just times the velocity of A. So that makes this problem much easier, because then we just have these three species instead. And if you notice that we have a VA here and a VA here, so when we solve for VA, velocity of A, we get the molar diffusive flux over the concentration of A. So this is important because we can now sub that up into here. So when we rewrite this equation, we now have the mass diffusive flux, little ja, is equal to the density of A times the molar diffusive flux over the concentration of A minus little v hat, which again is the average mass velocity. So after that, if you can tell, we can distribute this out. So we're going to distribute this out. Little ja is equal to density of, should be the density of A, apologize, over concentration of A minus density of A times little v hat. Now, what we have here is pretty neat. So this is the density of A over the concentration of A. So I want to first separate these two things just so I can show us something. The density of A is equal to mass over, just want to make sure this is still visible, mass over volume. The concentration of A is equal to moles over volume. So what happens when these two cancel out? We get mass over moles. That is the molar mass. So this all equals big MA, the molar mass of A. So by substituting these two in, by using this, we can see that these two things, the density and concentration over top of each other, equal the molar mass of A. So JA, if we rewrite this, substitute those two out, is equal to the molar mass of A times the molar diffusive flux of A minus the density of A times the average mass velocity. So the question is, next, what do we do with the average mass velocity right here? So the average mass velocity, I'm going to expunge on this function a little bit. So the average mass velocity is equal to the sum of all of the densities in the species. I have I here because it is a sum, times the velocity for each of these species all over the weighted density for the entire system. So when I expunge this out from the sum, we're going to get the density of A times the velocity of A plus the density of B times the velocity of B. And this is all over. I'm going to move this up a little bit so you guys aren't getting it bad in here. Let me move these lights. There's not as bad of a glare. The velocity of B. And then this is all over the total density of the entire species. So once we sub this in for here, I basically took the definition of it and expunged it out. So we're going to have the mass diffusive flux of A is equal to the molar mass of A times molar diffusive flux of A minus density of A all times this little monster right here. So inside there is the density of A. Again, velocity of A plus density of B times velocity of B. This is all over the weighted density for the entire system. So what we have here, we have everything all nice in densities and molar flux and molar mass and everything. We still have these velocities here. Well, we calculated the velocities earlier. So for the velocity of species A, it's going to be the molar diffusive flux of A over the concentration of A. And then for B, it's going to be the same thing, but just with B's. So we're going to substitute those in again. Give me a second to write everything down. So inside the parentheses, we're going to have the density of A times the molar flux of A, and this is going to be over concentration of A, plus density of B times the molar diffusive flux of B, and then this is over concentration of B. Again, this is all over the weighted density. Well then, if you remember from earlier, this guy right here, we have the density of A over the concentration of B, the density of B over the concentration of B. It's the same exact thing from this guy up here. So subbing these two out, we have density over concentration. That's going to give you the molar mass of A and B, respectively. So rewriting this yet again, minus the density of A, and then inside this guy, we're going to have the molar mass of A times the molar diffusive flux of A. I'm going to erase this a little bit. Plus the molar mass of B times molar diffusive flux of B. And then this is still all over weighted density of the whole system. So everything looks great. We're all in terms of A, except for this guy here, the molar diffusive flux of B. So how are we going to substitute this out? We're going to substitute this out because if you recall from earlier, this guy is equal to 0. So basically what that means is if the molar diffusive flux of A is all coming this way, something has to fill that void, so B is going that way. So with our key equations up here, I'm going to write that JA is equal to negative JB, or instead, for our substitution purposes, JB is equal to negative JA. So we're going to sub this guy in with just negative JA. So writing this one more time, the mass diffusive flux of A is equal to the molar mass of A times the molar diffusive flux of A minus A's density. And then inside, this guy is going to be the molar mass of A times the molar diffusive flux of A plus molar mass of B times, actually, it's supposed to be a negative sign because we're going to substitute this out with negative A. So that's going to be negative minus the molar mass of B times the molar diffusive flux of A, and then this is still over the density of the whole species. So if you can tell here, we have JA, JA, JA. We can sub out, move JA out of the equation. Is it possible to move this up without getting any more glare? Yes, so I'm going to write this equation down here. And then we also have, I'm going to substitute two things at once, but we also have the density of A over the whole density of the whole weighted species. So what that is that's just WA, because that's just the mass fraction of our system. So rewriting this one more time, we have the molar diffusive flux, the little JA is equal to the, I'm actually going to bring JA out, sorry, is equal to the molar diffusive flux of A, and this is Sorry, trying to do two things in my head at once. And this is equal to the molar mass of A minus WA, the mass fraction of A, because you have the density of A yet again over the density of the whole weighted species. So WA, and then this is going to be times the molar mass of A minus the molar mass of B. For a recap of what I just did here, I substituted out JA, undistributed that from the entire thing, and then changed the density of A over the total density of the whole system. That is the mass fraction. So this and this got turned into this, and then JA was pulled out of the entire equation. Just explaining my algebra real quick. This right here is what we are looking for. We have the mass diffusive flux of A, and that we have that relating to the molar diffusive flux of A, as well as the molecular weight of A, the molecular weight of B, and the mass fraction of A. This is what we're looking for. So before I wrap up the video, I just wanted to go over a couple of conceptual things. So this is the formula that we just derived. I still have the molar diffusive flux derivation here, and this is the mass diffusive flux right here. I just erased all of the algebra that led us to this equation. So to go over this again, we have the mass diffusive flux is equal to the molar diffusive flux times the molecular weight of A minus the mass fraction of A, and then in parentheses again, the molecular weight of A minus the molecular weight of B. So while I was getting taught this, I thought that, hey, a conversion between these two would be really easy. It's just going to be the mass fraction, because you're going from a mole amount to a mass amount. But after deriving out this entire equation, as you can see, the problem is right here, in that if you have different molecular weight of your two species, you're going to get a weight on your mass, your mass fraction. So if we, for example, had a molecular weight of A that was equal to the molecular weight of B, these two would cancel out to be 0. This would not mean anything, and then this would just equal the mass diffusive flux is equal to the molar diffusive flux, and then that's just going to be times the molecular weight of A. So if, hypothetically, you had two species where the molecular weights are the same, then this simplifies a lot, and the expression is just the mass diffusive flux of A is equal to the molar diffusive flux of A times the molecular weight of A, and then B as well, because they would be the same in this situation. But I just wanted to explain that conceptually a little bit, because during class I had a little bit of trouble conceptually thinking why that you just couldn't do the molar mass or the mass fraction and then go between these two. But after deriving the entire thing out, the molecular weights would have to be the same for that to happen. But this concludes my first video for Transport 2, homework number 1.